In this video we are going to discuss contingency tables, what they are and how can we use them. Contingency tables help us to deal with so-called categorical variables. The specialty of categorical variables is that they only assume a value from a predefined set of options, and this set is usually finite. These options are usually expressed as words or phrases, only seldomly as a number. You have probably came into contact with categorical variables many times in your life. For example, when you discuss the color of your car with someone, you were actually talking about the categorical variable. Other examples might include things like the brand of your laptop or the level of your education. Categorical variables are very common both in business and in research. Companies and scientists like to use surveys, and surveys are full of categorical variables. Many surveys contain so-called demographic questions. What is your gender? Where are you from? What is your occupation? And many of these demographic questions actually ask you about a categorical variable. Contingency tables help us to discover differences in the distributions or the frequencies of categorical variables between multiple groups that differ in some very important aspect. Let's have a look at some example. We are going to use the data from the Young People survey that is available for free on Kaggle. The two groups we will be comparing will be people from big cities and people from villages. Each group will have its own row in the contingency table. You can actually use the contingency table for more than just two groups, but we want the example to be simple. The variable that we are interested in this case is the smoking habits of these young people. We can assign four distinct values to this variable: never smoked, tried smoking, former smoker, and current smoker. Each value will have its own column in the contingency table. So now the question remains what we are going to put in the cells of the table. And it's actually pretty simple. All we have to do for the first cell is to count all the people from a big city that never smoked. The survey gives us the number 138. For the second column of the first row, we simply count the number of people who tried smoking and are from a big city. These criteria are matched by 303 of our respondents. And we can simply continue like this until the whole table is filled. The next step is to calculate the sum of each row. This gives us the total number of people from a city and the total number of people from a village. We also need to calculate the sum of each column. This gives us the total number of people who have never smoked, who have tried smoking, who are former smokers, and current smokers. Now we can simply add up all the column sums or the row sums to obtain the total sum or the total number of respondents in our survey. So now we have the full contingency table. But as I mentioned in the beginning, our goal is not to just create a table, but to use it to compare the two groups. The numbers in the contingency table indicate that there is actually not that big of a difference between people from a village and from a city when it comes to smoking habits. We can see that there are far more people from a city, so it's reasonable for us to expect that all the individual numbers for each type of smoking habits will also be larger. But if we look at the ratios between these smoking habits inside a certain group, we see that they don't differ that much. There are, for example, approximately twice as many people who have tried smoking as compared to the number of people who have never smoked. And it doesn't matter whether we are looking into the village group or into the city group. Of course, this, let's call it a see and tell method, is useful for, let's say, some initial ideas, but when it comes to really verifying that there is no difference, you need to use a statistical test. And the test we are going to use in this case is called chi-square test. And just with any other statistical test, the first thing we need to do is to define our null hypothesis and our alternative hypothesis. In the case of chi-square test, the null hypothesis is always that there is no difference between the groups. And you can probably easily guess what will be the alternative hypothesis, that there is actually a difference between the groups. The next thing we have to do is to define our level of significance. The level of significance basically tells us what is the probability that we falsely reject the null hypothesis even though it's correct. In our case, we are going to use the standard value of 5%. And now we of course have to calculate the test statistic. But before we can do that, in the case of a chi-square test, we first need to calculate the expected value for each cell of the contingency table. This expected value is usually denoted as capital E with two indices, I and J. I is the number of the row or number of our group, and J is the number of the column or the number of the specific value of our categorical variable. The first step to calculate this expected value is to calculate the ratio of each group in our survey. In other words, we are asking what is the percentage of the respondents that belong to each group. We can get this number by simply dividing the sum of each row by the total sum. By doing this, we can determine that about 70% of all the people who answered our survey are from a city. And of course, the remaining 30% are from a village. Now, to calculate the expected value for the first cell of the first column and the first row, we have to simply take the percentage from a corresponding row and multiply it by the total number of non-smokers. So what we are actually trying to do is to divide all the non-smokers in the same ratio as all the people in our survey are divided between cities and villages. And this actually makes a lot of sense. We basically expect 70% of all non-smokers to be from a city and 30% of all non-smokers to be from a village. Of course, given that there are no differences between these two groups. In our specific case, we have 207 non-smokers, and 70% of that is approximately 146 non-smokers who should be from a city. We can use the same formula to calculate all the other expected values in the contingency table. So for example, let's take the villagers who have tried smoking. There are 429 people who have tried smoking in our survey, and about 30% of all the respondents who answered the survey are from a village. So we just multiply these two numbers, and this gives us the expected number of people who are from a village and who have tried smoking. And now we can continue like this until we calculate the expected value for each cell of the contingency table. Now, if we want to be a bit more exact, here is the precise formula how this is calculated. So, to calculate the expected value for the row I and the column J, we take Tj, which is the sum of a column, and then we multiply it by the ratio between the sum of a row and the total sum. This is the percentage we have talked about. Now we can actually use this expected value to calculate the test statistic. We start by simply calculating the difference between this expected value and the real value we actually obtained from the data. Just to provide an example, if we look at the village never smoked combination, we can see that the value 7.61 is calculated as the difference between 69, the real value, and 61.39, the expected value. It actually doesn't matter what is the order of numbers when we are doing this subtraction, because in the next step what we do is that we square this difference up. What we are interested in is actually the magnitude of the difference. not really the sign. We are not interested in whether the difference is positive or negative. Okay, so now we take this square and we divide it by the expected value. This kind of normalizes the value. Just to show you why we are doing this, let's pretend that suddenly we have 10,000 respondents in our survey. So the differences or the squares of the differences actually go up. But this doesn't necessarily mean that this bigger survey actually contains more differences between the groups as our small survey. Since both surveys have different numbers of respondents, we kind of have to get them to the same level. And we do this by dividing the difference or the square of the difference by the expected value. And finally, the last thing we do is that we add all these numbers together. And that's it. We have calculated the value of our test statistic. Now there is this last teeny tiny number that we need to calculate before we can actually perform the test, and that is the number of degrees of freedom. I might have a deeper look at the concept of degrees of freedom in another video, but for now all you need to know is that for you to calculate the degrees of freedom in the case of a chi-square test, you just multiply the number of rows minus 1 times the number of columns minus 1. So in our case we have 2 rows minus 1 times 4 columns minus 1, which is of course 3. So just to kind of orient ourselves, what we are doing is that we are performing the chi-square test. We have our hypothesis, we have our level of significance, we have calculated the test statistic, and we also know the number of degrees of freedom. The next thing we need to know is the so-called chi-square distribution. So what this distribution basically tells us is how the test statistic, the value of test statistic, would be distributed if we, let's say, repeated the same exact test 1000 times. So we would basically do this survey over and over again and calculate the test statistic over and over again. So we would end up with multiple measures of the test statistic. If we plotted all of these measures as a histogram, we would obtain something very similar to this picture. This is how the values would be distributed. Of course, there is one important assumption. This would be true only if the null hypothesis were correct. In other words, only if there were no differences between the groups we are comparing. Now, what we do with this distribution is that we divide it into two parts, and we use our level of significance for that. Since our level of significance is 5%, we divide the distribution such that the white larger part will contain 95% of all the measurements, and the smaller red part will contain the remaining 5%. So, if the null hypothesis were correct and we calculated the test statistic, it would be very likely that our result would be somewhere in the white part. On the other hand, there is only 5% chance that our result would be in the red part. And exactly because this second scenario is highly unlikely, when our test statistic actually falls into this part of the distribution, we say that we actually reject the null hypothesis. But before we can reject anything, we first need to divide the distribution into these two parts. So how to do that? Well, we of course need to find the number on the horizontal axis that actually splits the distribution. And this value is called the critical value. One way to find it is to simply use Microsoft Excel, Google Sheets, or some similar program. Most of these editors have a function called chi-sq.inv. It takes two arguments. The first one is the size of the white part of the distribution. In other words, 1 minus the level of significance. And the second argument is the number of degrees of freedom. In our case, the white part will represent 95% of our distribution, and we have 3 degrees of freedom. The result the function gives us is 7.814, and this is exactly what we need. It's the point on the horizontal axis that divides the distribution into those two parts. When we have this number, this critical value, all we need to do is to compare it with our actual test statistic. If our calculated test statistic is greater than this critical value, it means that we actually reject the null hypothesis. But our case is actually the opposite. The value of our test statistic is less than this critical value. This means that we actually can't reject the null hypothesis on a given level of significance. If we speak a bit more practically, this means that we can consider both groups as equal when it comes to smoking habits. We can arrive to the same conclusion by calculating the p-value. To do so, we can again use a function offered by Excel or any other sheet editing software. The function we will use this time is called chi_sq.dist, and it takes 3 arguments. The first one is the value of our test statistic, the second one is the number of levels of freedom, and the third one is set to 1. To get the actual p-value, we have to subtract the value we obtain from this function from 1. In our case, we get the p-value of 0.524. This means that about 52% of all the critical values we would calculate if we repeated the test many times, as I explained earlier, would be greater than the actual test statistic we calculated in this case. Of course, given the null hypothesis is correct. After we calculate the p-value, we can compare it to the level of significance. If the p-value is greater than the level of significance, which is also our case, it means that we can't reject the null hypothesis. On the other hand, if the p-value was less than the level of significance, we can reject the null hypothesis. Okay, so what is our conclusion then? Both the critical value and the p-value show us that the null hypothesis can't be rejected. This means that both people from a city and people from villages have similar smoking habits. So, just to recap, we took a real survey data about the smoking habits of young people, and we transformed this data into a contingency table. Then we wanted to find out whether there are some differences in the smoking habits of people from a village and people from cities. We used the chi-square test for that. We were able to calculate the test statistic and then used it to conclude that both of these groups are very similar when it comes to smoking habits. And this is the end of this video. I hope it helps you during your studies, or even better, to solve a real problem.